Imagine a metal so powerful it defies gravity, bending the laws of physics to fuel extraterrestrial spacecraft. Bob Lazar, the controversial whistleblower, claims to have worked on such alien technology at a secretive site near Area 51. At the heart of his explosive revelations lies Element 115, a mysterious substance supposedly capable of enabling interstellar travel. Is it the key to unlocking advanced propulsion systems, or just a fragment of conspiracy lore? Dive into the claims, science, and intrigue surrounding this enigmatic element and decide for yourself, hoax or harbinger of humanity's future among the stars. Welcome to this fascinating exploration of Element 115, known to scientists as Moscovium. In today's discussion, we'll uncover what modern science tells us about this elusive element and evaluate the bold claims made by Bob Lazar. Specifically, we'll examine its potential for energy release in nuclear reactions, its possible use in antimatter reactors, and the extraordinary suggestion that it could manipulate gravity. Let's start with what we know for sure. Moscovium is a synthetic element, meaning it doesn't occur naturally. It's classified as a super-heavy element with an atomic number of 115. However, its existence is fleeting. Its half-life lasts only a fraction of a second, making it highly unstable. Most importantly, no stable versions of Moscovium have ever been observed or created in laboratories. Yet Lazar's claims rest on the premise that a stable version exists, one with extraordinary properties that could revolutionize energy production and physics itself. If such a stable version existed, it could release immense energy through nuclear reactions, following Einstein's iconic equation: energy equals mass times the speed of light squared. This equation calculates energy from the mass difference or mass defect in nuclear processes. To give you a sense of scale, typical nuclear fission or fusion reactions release energy equivalent to about 100 million joules per gram of material. Even this is a staggering amount of energy when compared to most conventional fuels. Lazar goes beyond conventional nuclear science, proposing that element 115 could be used in an antimatter reactor. In such a system, matter and antimatter annihilate, releasing all of their mass energy. For context, a single gram of matter-antimatter annihilation would unleash about 90 trillion joules of energy. That's equivalent to the explosive power of over 20 kilotons of TNT, roughly the size of the Hiroshima bomb. Perhaps the most extraordinary claim is that element 115 generates its own gravitational field. If true, this would require entirely new physics, going far beyond the standard model. Such a discovery could revolutionize space travel, allowing spacecraft to warp space-time itself. However, no evidence or plausible mechanism for this gravitational effect has ever been provided. To evaluate these claims, several major assumptions must hold true. 1. A stable version of Moscovium must exist, with properties beyond what has been observed or synthesized. 2. Antimatter production must become significantly more efficient than current methods, which are extremely energy-intensive. 3. Gravitational manipulation, using element 115, would require an entirely new framework of physics, one we have yet to discover. In summary, while the theoretical energy potential of a stable Moscovium isotope or antimatter reactions is immense, these claims remain speculative and unverifiable with our current understanding of physics. Let's explore the energy released during a fission reaction, focusing on a hypothetical scenario involving element 115, without assuming any antimatter reactions. At its core, nuclear fission occurs when a heavy atomic nucleus splits into two or more smaller nuclei. This splitting process releases energy. The source of this energy lies in what's known as the mass defect, the difference between the mass of the original nucleus and the total mass of the smaller nuclei created in the reaction. To understand the energy released, we look at the binding energy of the nucleus, which is the energy holding it together. For most heavy elements, such as uranium and plutonium, the binding energy is about 8 million electron volts per nucleon. When a heavy nucleus undergoes fission, only about 0.1% of its total mass is converted into energy. While this might sound small, the resulting energy is enormous when scaled up due to the immense energy potential locked within atomic bonds. The nuclear mass defect is the difference between the actual mass of a nucleus and the total mass of its individual protons and neutrons if they were considered separately. To put it simply, it tells us how much mass is missing when the nucleons, protons and neutrons are bound together in a nucleus. Here's how we calculate it. We start with the total mass of all the protons in the nucleus. This is found by multiplying the number of protons, represented by Z, by the mass of a single proton, which we'll call m sub p. Next, we add the total mass of all the neutrons. To find this, we take the neutron number, n, and multiply it by the mass of a single neutron, m sub n. Finally, we subtract the actual mass of the nucleus, represented by m altogether. The mass defect equals the proton number times the proton mass, plus the neutron number times the neutron mass, minus the actual mass of the nucleus. The proton number, Z, is the same as the atomic number of the element. It tells us how many protons are in the nucleus. The neutron number, N, is the total number of neutrons. We can also calculate N as the difference between the mass number, A, which is the total number of protons and neutrons combined, and the proton number, Z. The masses m sub rho and m sub n are the standard masses of a proton and neutron, respectively. If we know the values for Z, n, m sub p, m sub n, and the nuclear mass m, we can calculate this missing mass, or defect. The nuclear mass defect corresponds to nuclear binding energy. This is the minimum energy required to break the nucleus apart into its individual protons and neutrons. To convert the mass defect into energy, we use Einstein's famous equation, E equals mass times the speed of light squared, which tells us that mass and energy are interchangeable. In summary, the nuclear mass defect helps us understand how much energy is needed to hold a nucleus together. It's a powerful tool for exploring the forces at play inside the tiny world of the atom. Now, let's consider the case of element 115. If we assume that a stable isotope of element 115 exists and behaves similarly to uranium-235 or plutonium-239, we can estimate its energy release during fission. The atomic mass of this hypothetical isotope is roughly 288 atomic mass units, based on estimates for moscovium isotopes. During fission, each nucleus would release energy equivalent to around 200 million electron volts. In this segment, we'll walk through the step-by-step calculations for the energy released during the fission of element 115. I'll explain the math in plain English, so it's easy to follow. Let's dive in. First, we start with the energy released by a single fission event. Each fission reaction releases about 200 million electron volts of energy. To convert this into standard units of energy, we use a conversion factor. 1 million electron volts is equal to approximately 1.6 times 10 to the negative 13 joules. So, to find the energy per fission, we multiply 200 million electron volts by 1.6 times 10 to the negative 13. This gives us approximately 3.2 times 10 to the negative 11 joules of energy released by a single atom undergoing fission. Next, we calculate how many atoms of element 115 are in 1 gram. To do this, we divide Avogadro's number, roughly 6.022 times 10 to the 23rd atoms per mole, by the atomic mass of element 115, which is approximately 288 atomic mass units. Performing the division gives us about 2.09 times 10 to the 21st atoms per gram of element 115. To find the total energy released by 1 gram of element 115, we multiply the number of atoms in a gram by the energy released per atom. This is 2.09 times 10 to the 21st atoms multiplied by 3.2 times 10 to the negative 11th joules per atom. The result is approximately 6.69 times 10 to the 10th joules released by 1 gram of element 115. To put this into perspective, the energy released by 1 gram of element 115 during fission is equivalent to the energy of about 16,000 kilograms of TNT. That's an incredible amount of energy packed into just 1 gram of material. To put this in perspective, that's comparable to the explosive energy of around 16 kilotons of TNT, which is similar to the energy released by the fission of uranium or plutonium. When a single atom of uranium-235 undergoes fission, it releases about 200 million electron volts of energy. For simplicity, we'll use the abbreviation MeV for million electron volts. Now, to convert this energy into the more familiar unit of joules, we use a conversion factor. 1 MeV is equal to 1.6 times 10 to the negative 13 joules. So, multiplying 200 million electron volts by this conversion factor gives 3.2 times 10 to the negative 11 joules per fission reaction. To calculate how many uranium-235 atoms are in 1 gram of the material, we use Avogadro's number, which is approximately 6.022 times 10 to the 23rd atoms per mole. The atomic mass of uranium-235 is roughly 235 atomic mass units, which tells us how many grams are in 1 mole. Now, dividing Avogadro's number by the atomic mass gives us about 2.56 times 10 to the 21st atoms per gram of uranium-235. Next, we calculate the total energy released when 1 gram of uranium-235 undergoes fission. To do this, we multiply the number of atoms in a gram by the energy released per fission reaction. The number of atoms is 2.56 times 10 to the 21st, and the energy per atom is 3.2 times 10 to the negative 11th joules. Multiplying these together gives approximately 8.19 times 10 to the 10th joules per gram of uranium-235. To put this into perspective, the energy released by 1 gram of uranium-235 during fission is roughly equivalent to the energy released by 19,500 kilograms of TNT. Why does uranium-235 release more energy than the hypothetical element 115 in a fission reaction? Let's dive into the physics behind this phenomenon. Here's why. Uranium-235 has a lower atomic mass, about 235 atomic mass units, compared to element 115, which is around 288 units. This means that for the same mass, there are more uranium-235 atoms available for fission. 1 gram of uranium-235 contains about 2.56 times 10 to the 21st atoms, while element 115 contains only 2.09 times 10 to the 21st atoms, 21 atoms. Despite similar energy per fission, uranium-235's higher atom density allows more reactions, leading to greater total energy release. Additionally, while uranium-235 is well studied and used in reactors, element 115 remains theoretical with limited practical application. Bob Lazar claims that element 115 is the key to operating UFO reactors, enabling them to manipulate gravitational fields. According to his theories, this element acts as a power source capable of generating the immense energy needed for such advanced technology. However, a key issue arises when we compare the energy release of element 115 with that of uranium-235, a well-known source of nuclear fission energy. Our calculations show that uranium-235 releases significantly more energy per gram during fission than element 115. This is due to uranium-235's higher binding energy per nucleon, meaning that when it undergoes fission, more energy is released. In contrast, element 115, with its slightly lower binding energy per nucleon, results in less energy being released during a similar process. This disparity is concerning. For a power source to effectively fuel technologies like UFO reactors, it must release an enormous amount of energy efficiently. Uranium-235, with its higher energy output, seems more suitable for this purpose, especially from the perspective of traditional nuclear fission. If element 115 cannot release as much energy, it raises doubts about how it could power such advanced systems. This creates a gap in understanding Lazar's description of element 115. If it truly powers UFO reactors and manipulates gravitational fields, we'd expect its energy release to be similar to or greater than uranium-235. Yet, the evidence points to a much lower energy yield, raising questions about the practical application of this technology. In summary, while element 115 is fascinating and has sparked much speculation, its relatively low energy release compared to uranium-235 creates a significant challenge in understanding how it could fuel UFO reactors and manipulate gravitational fields, as Lazar claims. Until this issue is resolved, the practicality of element 115 in such advanced applications remains highly questionable. So, if element 115 releases less energy than uranium-235, what makes it the key to UFO reactors and gravity manipulation? Bob Lazar claims it releases gravitons, particles that could control gravity itself. If this is true, element 115 might not rely on traditional energy release, but instead taps into a new aspect of physics, allowing for gravitational control. This raises a huge question. Could element 115 be unlocking secrets of gravity we haven't discovered yet? If it truly releases gravitons, it could revolutionize our understanding of energy, propulsion, and the very forces that govern the universe. Could this be the breakthrough that changes everything, or is there something we're missing? The answer may lie in a science we've yet to fully explore. If you're as intrigued as we are about element 115 and its potential to manipulate gravitational fields, you won't want to miss our next video. We'll dive into the science of graviton production and how element 115 could play a role in amplifying these elusive particles. Join us as we explore the cutting-edge theories that could unlock the mysteries of advanced propulsion technology. Make sure to hit that subscribe button and turn on notifications so you never miss an update. See you in the next video.